All right, so welcome everybody to today's deep dive talks in data-driven fluid mechanics. Hello to the virtual community in YouTube and Zoom. So today we have two talks as usual. The only difference that in this afternoon we will have the talk at a different time. It will be at 3:30. So just keep that in mind. So today we are going to have a talk now from Sam Taira, who's a professor in mechanical engineering and aerospace engineering in UCLA, University of California, Los Angeles. And he's going to talk about towards the analysis and control of extreme aerodynamic flows. So Sam, over to you.
Good morning. And first, thank you, Luca and Karthik, for organizing this wonderful workshop. I've been having a great time. So today, I'm going to talk about what we call extreme aerodynamic flows. And you see the movie in the background. There's going to be a lot of vortices hitting the wing. And these are situations that we humans probably don't want to be flying in, but I'll explain why we're interested in this. Let's see. This to work. Okay, before I get started, let me thank a few people or several people who've been involved with in this project. You're going to hear a lot of work that's actually been led by Kaif Kami, who is a graduate student about to graduate in about a year or so. Yonghong, Vedasri, Luke, or current members of our group, students in postdoc. Aditya and Xian have worked on this, and they've graduated and hence since become faculty members at other universities. And we have our collaborators on the bottom row. You're going to see some work that we've done with Steve, and also some experimental data analysis from Anya Jones's group from the University of Maryland. And I have to thank a lot of our sponsors from the DoD side, and this effort was actually funded heavily by the Vannevar Bush Faculty Fellowship Program. Okay. So we've heard a lot about coordinates in the past few talks, and this talk is no exception here. So here's a cartoon. I was told to put in a sort of a tutorial, so this is my very short tutorial, right? So if you have a signal that seems somewhat complicated, but we know this nice tool called Fourier analysis. So if you know how to decompose the flow, and if you know how to represent this complicated looking signal on the left, this is a very easy problem, right? Suddenly, if you were to plot this signal using the coefficients for these three functions, now this signal just becomes a point, and now simple, right? A lot simpler than looking at this signal. So that's what we're going to want to do for fluid flows in general. And by the way, the labels are kind of off. Those are the coefficients of those sines and cosines, but everybody gets the point. Okay. Now, what have we been doing? We have favorite compression techniques. So in the past, there's been a lot of efforts that's looked into modal analysis techniques, including POD and DMD. So if you were to, let's see if this works. Here we go. If you have a fluid flow, and if you have a collection of those, we can actually go through the mechanism or sort of the routine of POD type analysis, decompose it into mean and modes. And if you were to have dominant modes, you can keep up to a certain point, certain modes, and truncate, right? And if that's enough, hopefully you'll get a reconstruction that looks fairly good for your need, right? If you need more, you can, of course, add more. So these are linear techniques, right? Now, what I'm going to talk about today are nonlinear techniques. And I'll talk, in particular, we've heard talks on autoencoders. This is no different. I'm also going to talk about how to use an autoencoder, but what's unique about this talk is perhaps how we view autoencoders in terms of compression. Just a little interesting side note here is that there is also a lot of image and video compressions that are being developed in, let's say, in the film industry or also in multimedia industry, billion-dollar industry, and they work really well. So for anybody who's interested in actually going beyond standard techniques to compress, especially videos, there's some really amazing techniques out there. And software companies such as CFD simulation companies are interested in using these as a way to save data, which is actually, I think, incredible. Okay, all right. So let me now get into the physics side of why we think this is an interesting problem. And I think this is a really great problem to demonstrate the capabilities of data science techniques. I'll explain why. So you might see these in the news, right? And you might have been uncomfortable flying when there's a lot of what we call severe turbulence, right? And they say it's about to get worse. I'm actually not going to talk about this. This is okay. You spill your coffee, maybe you're going to hit your head against a wall. That's fine. You're not going to die. The airplane's not going to break. What I'm going to talk about is, here's a cartoon of it. I'm going to talk about airplanes that are much smaller in scales that might be flying in a more dense environment, such as in between buildings or in a mountainous area. Maybe you're trying to land these vehicles behind a ship. Now, if you think about these situations, you're going to be flying in the wake of either a natural structure or a human-made structure, which generates a wake. So if you think about this, the size of the wake or the vertical structures in the wake could be about the size of the vehicle itself, the flying body. And this is where it becomes a little tricky, right? What we call the gust, the vortex gust, or these gusts could be on the same order as your flying velocity, right? The translational velocity. Currently, if you go to a textbook, there's really not a lot of description on this. There are some gust response or gust rejection textbooks in the aeronautics sector. And if you look at those gusts are really small. Okay? The ones that we feel uncomfortable, it turns out to be not that big of a deal. So here, what we're going to try to do is to actually take advantage of data-driven methods to see if we can expand and extend our current understanding of aerodynamics to situations where we traditionally avoided operating aircraft. Right? So you might have heard in the news, helicopters won't go and rescue someone because it's too windy. Those are situations that we're thinking of and maybe even beyond. So let me talk about this a bit and why it's complicated. This is what we're used to seeing. This is what I call steady aerodynamics. You have a base state, for example, something like cruise. And you might have some perturbations. You might be flying into turbulence. So you might see some fluctuations about the base flow. We actually know how to do this pretty well. So most of you have flown here or have flown in the past, and this is no different. Now, if you're a bit more adventurous, you can fly into an unsteady environment. This is what I would call quasi-steady aerodynamics, where you have the base flow that's changing. For example, if you're hunting a hurricane, or if your vehicle geometry is changing over time, then you would have some base state that is changing over time, and you might have perturbations around it. This is also still manageable. We still have these aircraft flying and doing some pretty awesome things. Now, where it gets tricky is these situations, where you would have the base flow that's changing and the disturbance that is also changing on a similar time scale and also on a similar spatial scales, which is encountered in these situations. For example, if you try to land a helicopter behind a structure or behind a ship, if the wake of the ship is pretty sizable, you can imagine that the helicopter is actually smaller than the wake itself, right? So now, I mean, the way I think about it is, we used to think of a wing being hit by a perturbation, but the aircraft itself might be the perturbation if you think of the wake as being there, right? And the wake is being perturbed by the aircraft. So it could be the other way around in some extreme cases. So this is what we call extreme dynamics in our group and what we're working on. And if I may borrow a figure from Anya Jones's annual review article, you can actually define a gust ratio, which is a characteristic velocity of the disturbance or the perturbation, which we'll talk about much more later, divided by the free stream velocity. And if you look at, for example, here is a commercial airliner, you're flying pretty high and the gust velocity is really slow. In that case, the gust ratio that they would encounter is extremely tiny, right? But if you go to a smaller scale vehicle or say a flying insect or an animal, it is possible that even for a small gust, because the translational speed being so low, the gust ratio that you're going to encounter could be on the order of 0.5 or 1. Now, as you go towards this direction, you would have higher gust ratio, and typically we will not fly, or you won't see things flying at a gust ratio exceeding 1. In this talk, we're going to be talking about gust ratio exceeding well over 1 and closer to 10. right, which will be if you were to fly in a very gusty condition over here, which does happen in urban canyons, urban environments, right, between buildings. Okay, so why is this challenging? Simply put, it's because you cannot distinguish the base flow and the disturbed flow easily. You can't decompose the two. So the amplitude of the disturbance is so large that linear theory is not expected to be valid. Right? This is not. In some cases, it turns out for a lower size aspect gust ratio, linear theory could still be taken advantage of, and it works to some extent. But as you'll see later, linear techniques is probably not going to work very well for the problems that we're going to be seeing. Okay, so we're going to have to come up with some unique ways to first model, characterize these flows, and hopefully control it. And so this is year one of our effort, and you're going to see that we're making some headways toward modeling and analyzing this flow. You'll see later, and we're thinking now about how to control or maybe even stabilize flight. But that also needs to be revisited in terms of the concept of flight. Okay? So let me explain the model problem first. The model problem we're considering is a two-dimensional airport flying at various angles of attack. It is laminar in 2D, at Reynolds number 100. But if you think about this problem, because this wing is going to be, let's say, going through some disturbance, and the local acceleration or the temporal acceleration that it will feel is so strong, the amount of vorticity that it's going to generate as it's flying through these disturbances is, because it's so large, it's going to have a lot of laminar effects. So we're actually okay with first studying laminar flow. Okay. However, the bigger problem is actually the following. There's a huge parameter space that we have to go over to understand this physics. So this is just simply a vortex hitting a wing. However, the strength of the vortex, the size of the vortex, the position at which the vortex hits the wing, we don't really talk about this too much, but the profile of the vortex, right? Now, if this was, this is all on the vortex side, the vortex disturbance side, but also on the airfoil side, there's the angle of attack, airfoil shape, the timing at which the vortex hits the wing. Those are also important. And we can actually go beyond and say, what about the Reynolds number effect, the Mount number effect, the effect of noise? Those effect of noise we'll consider, but here we're going to fix the Reynolds number to 100 in an incompressible region. Okay? If you think about this in 3D, this gets even worse, right? If you think about flying in a sea of vortices, these vortices, the orientation could be at different angles, and you might be flying through it, right? It may not always be a two-dimensional problem. Okay, so what does this translate to? It really translates to a huge data set. This slide itself is like 100 megabytes, just a movie, right? This is what Kai generated. But let me explain what these figures actually show you. Each of these three-dimensional plots are for different angles of attack. Here is the location at which the vortex hits the wing, so the vertical location. D is the size of the vortex in relationship to the chord. G is the gust ratio. Okay? We actually have a lot more data. We're only showing training data sets from -4 to 4 in terms of the gust ratio. These are pretty small. These are pretty extreme. You wouldn't want to be flying this kind of condition. And each point is just a case. So each case has hundreds and thousands of snapshots that we will have to go through. So you can imagine this gets really expensive pretty quickly. Now, if I were to just extract some of the snapshots from this study and put it for, let's say, angle attack of 20, 30, 40, 50, and 60 degrees, we call time of zero the time of the impact. So this is when the center of the vortex is aligned with the leading edge of the wing. Over here on the left-hand side are the wakes without disturbances. Okay, so these are the sort of the reference baseline cases. At higher angles of attack, you'll see in shade. And on the right are some of the snapshots that you'll see, representative snapshots, when the wakes are being drastically modified due to the impact of the vortex, or maybe shortly afterwards. And you can see that they're all over, right? In the sense that they look quite different from one to another. Now, if you also look over here on the left, this is the lift profile. experienced by the wing. And if you look at this, these dashed lines are the baseline cases. So those are about order 1 in terms of where they are. And because these vortices, because these are so strong, lift is increased by almost tenfold in a very transient. So this is a very violent flight, I would say, situation, right? You really wouldn't want to be flying in this way. All right. Well, let me also add a note. Although this might look a little, let's say, daunting because there's a lot of features, different features in the flow, one of the things that's nice is that us fluid mechanicians can actually recognize the dominant features with our eyes. For example, the vortex, leading in shear layer, starting to roll up into vortices. There's another vortex over here, there's another vortex over here. These are features that we can identify with our eye. So my understanding or belief is that if these are the types of flows or features that we can understand with our eyes, perhaps we have hopes in having machines or these algorithms pick up these features in a similar manner that we would be able to. Okay? Okay, so before I go further, let me first start by attempting to analyze this flow with POD. And you might say, well, Sam, that's going to be fantastic because it's going to fail fantastically, and it will, okay? So I'm just going to show you the variations of the temporal coefficients of all the cases that we collected, like perturbed, unperturbed, everything. Right? And here, I'm only going to show you the first 3 coefficients, right? And it won't need a lot more than 3 to capture all the fluctuations in the entire flow field, but just for demonstration purpose, let me show you how messy it is. These gray lines are basically plotting all the cases that I showed on the previous slide. And these colored lines are actually the baseline cases without, or the reference cases without being perturbed. Okay? It's a mess, right? To make it even more, well, what's worse is actually the reconstruction of the flow field is really bad, right? This is the sort of what we want to reconstruct. The big vortex about to hit a wing at 60 degrees angle of attack. First of all, it doesn't even reconstruct the existence of the vortex that's about to hit it. And because this is a linear technique and we're training it with 6 different angles of attack, 60, 20, 30, 40, 50, well, that's 5 actually, I apologize. You can actually see the reminiscence of the bases, right? Because it has kind of like this shadows of the wings. Right? So it just, go ahead. Oh, yeah.
Sorry.
Go ahead.
Are you recommending mean or
Yeah.
how do you define it?
Yeah.
Mean across all the cases?
Yeah. But
That's
it just,
not one of these.
hmm?
So that's not in that 3.
No. So you just can't get this, right?
Right.
This is really, well, it's not supposed to, I guess. It's not supposed to. I mean, you could do some clever things and try to shift all this and so that the wing doesn't look like it's in motion, but that defeats the purpose, right? So, and this is the amount of error. This is 130% error, 128% error. It just doesn't do well. Okay, so.
You satisfy the no-sleep condition you encountered?
Pardon?
You satisfy the no-sleep condition on the surface of the body with the theory?
Because we're actually providing wings at different locations, right? We're not shifting it all to be at the same location. I don't think the no-slip is not going to be satisfied. So,
But then how do you satisfy the right production of electricity? How do you guarantee the right production of electricity for the theory?
we're not guaranteeing anything. This is just straight out POD. This is just post-processing. Right? We're not trying anything super clever or trying to do anything. We're just saying, take all the data and just perform POD. Okay? Now, what we tried was then a nonlinear compression using an autoencoder. On the input, we're going to take all the flow fields that we collected on the vorticity side, right? And then we're going to try to generate the same thing, where in the middle, you have this kind of a bottleneck. So over here, you have an encoder that tries to shrink the dimension of all this input, right? Using a convolutional neural net, because we want to handle this two-dimensional data, and then you're going to connect it with a multi-layer perceptron in the middle. Then you're going to have sort of the mirror image on the other side, which will be the decoder, right? So you'll start with NLP, and then you're going to get it to the right size using a CNN. And here, we're just trying to minimize the difference between the input and the output and try to figure out how to tune the weights in the middle. And one thing I wanted to sort of note is that here, the variable xi in the middle, and you'll see that it's actually, we try to shrink it to 3 here, is what we call a latent space variable, the right coordinates, as we'll discuss later. And we're going to see what this means, right? So if the compression is done right, it will go to a small variable and it'll come back to the large variable again, and you won't lose too much information. And the nonlinearity comes in the activation function here, right? And here's what we get. If we just do a straight out autoencoder compression, we get this math. Now, is it better? I don't know. It looks like a big mess to me still. But what's nice is that you actually get to predict the flow. Right? Now, what's amazing here, and we were kind of pleasantly surprised, is that we only need 3 variables.
Are you predicting or are you reconstructing?
Reconstructing. We're not doing prediction. This is
what a distinction.
It is an important distinction. Just 3, right? So what that means is all the flow field features that we've got, right, that we collected, can now be compressed to just 3 numbers, which is, to me, super important. Now, one thing I still don't like, is I don't like this, because I don't understand what this means. This is all over the place. There's a big scatter of data. So this is when we started to think about how we incorporate physics, right, physical information into the autoencoder compression.
What's the accuracy in the force reconstruction?
We can talk about it. It's actually about the same order. But let me actually, force reconstruction is actually not bad. It's actually pretty accurate. But let me talk about this. We want to do better, and we want to understand certain types of physics that would appear in this type of extreme flows. And this is how we supplemented the training process. We said, what we really care about this whole exercise is, again, hopefully how to fly, and lift is an important variable. So as we go through the training process, we wanted to make sure this latent space variable, the coordinates, right, xi, retains information so that it can reconstruct the lift very well. So in the training process, there's also the minimization for lift. But this actually works really well, because if you think about this, this also implicitly weighs structures that are important in generating this transient lift. Right? Furthermore, if you recall how large lift is, lift went up by about 10-fold, right, by an order of magnitude. So if you want the transient physics to be captured, this is actually turns out to be a pretty nice way to incorporate that transient physics so that these weights are tuned to capture transient dynamics well. Right?
So only 3.
We tried a lot.
So there's some tuning in this. So the story is very much preferred.
So we actually went from, I'll talk about why 3 seems to be a good number. We actually tried with like 6, 5, and it was more like a reduction process to how far we can reduce it. And 3 seems to be the minimal that we can go down. So there's a bit of a trial and error process. I'm not going to lie to you that getting to this structure was not like a walk in the park.
So there are 2 ways of going about that process.
Mm-hmm.
One is you go from a latent space to your full flow field, compute pressure and skin friction, and then compute lift.
Absolutely.
But you're putting psi to a neural network to get there.
Mm-hmm.
So you're not like integrating the pressures and friction.
No, we could do that. I mean, this is not like a unique variable, right? You can actually choose the right variable to go through this exercise. If you want this xi to retain certain information. There also is discussion that we had about, should we have lift be fed in, right? Or we chose to do it this way because we wanted Zai to, as it goes through this exercise, explicitly spit out.
But what if you had just done a calculation of lift from the flow field?
I don't think it's going to be that accurate, to be honest with you. No, I haven't tried it, or Kai hasn't tried it. Maybe he has.
Yeah, but that could be
That could be another way to do it.
yeah, another way.
In fact, we could also try to constrain that.
Yeah.
That's actually maybe. Okay, now if we try this, it gets interesting. We get this. So all that mess that we had, and by the way, now we get this structure. And Petros actually has seen an earlier version of this, and Petros, I'll make this note just for you. Earlier when we tried this, we actually just tried to put in a shape that it conforms to. Now we don't do any of that. So this just comes straight out of that optimization or sort of the training process, right? And of course, these solid colored lines are the cases without any disturbances, right? So now, Rich, you asked us, or you asked me, why 3, right? Actually, it could be 2, but I'm going to keep it as 3. Because this axis, Xi3, tells you the angle of attack or the effective angle of attack that the wing feels as it's being hit by the vortex. Xi1 and Xi2 are actually needed to define the phase dynamics as it's oscillating. Where oscillating is kind of a stretch when you have a transient physics, but I'll actually get to that later. So you need actually 2. Now, if you look at the flow field, the error actually goes a little higher, but not much, but you can actually get the flow field pretty well too. And Petros, to answer your question, actually the lift prediction is pretty well too. Let me see. And this is for Peter. Oh, wait. This shape, we call it cone shape. But in the Japanese language, we call this the triple cornet, which probably is related to the cornet. So it has that shape, right? It resembles that shape. So we
What
call it.
happens if you put the fourth arrow in your Latin?
You can actually do well with the reconstruction, but it's very difficult to understand what the fourth axis means. So
Have you done that?
yeah, we've done it. Yeah.
And what does it do?
You can actually plot 3 axes and it gives you a similar shape, and you can improve the. I believe you can improve the reconstruction slightly, but it doesn't seem to be that
Use much for the fourth one.
I don't think so. To be
So
honest.
it's captured after 3.
Yeah.
If you increase the Reynolds number, you need 3.
I'm sure we'll need more than 3. We haven't gone there yet. Yes.
When you're trying to reproduce the flow, is it just an initial snapshot of the vortex into the aerofoil, or it can't be the whole evolution?
It's a whole evolution.
Whole evolution.
Whole evolution. This is pre-amazing. 3 variables, whole evolution. I'm not just talking about one flow field versus one flow field only. This is the entire collection of vortex hitting a wing. Sometimes this air will go up and down, expected. But overall, we can actually do a pretty good job of estimating where the vortices are and what the wake will be.
So you take the time to sort of vortex appearing from the left, going out the right.
Okay.
This is just a snapshot, or you have a video?
I don't have a video right now, but this is just a snapshot, but we can prepare a video too. Now,
No, but you capture the flow.
instantaneously, constantly. Now, I'll get to that because right now this is just the autoencoder. You have flow coming in and you have flow going out. And I'll just make a remark towards the end of it. Now, Richard asked, why 3? It turns out it's actually not 3 because if you know what this, and this is actually an old side, this shape isn't exactly right, it's more of a cone shape. But if you actually know what the shape of this manifold is, this cone manifold, you can just project it onto this manifold and, for example, think of it as just looking down on the 3rd axis and projecting it, and you'll get a phase space portrait. And I actually like this quite a lot because in the middle is where you have steady flow without any shedding, And if you just look at the undisturbed case, this is just an oscillator. You have the leading edge vortex forming and the trailing edge vortex forming, and it shares alternating fashion, and it goes through these circles. The higher the angle of attack, the vortex is of course larger, so the radius increases, right? Now, if you perturb this, you'll be set off from this limit cycle, and you go outside and you can come back in, because after the vortex is flushed out, it will go back to the original limit cycle. So to me, this makes sense, right? This is a very easy way for me to see how the dynamics evolve, and it's kind of a nice way for me to get out of looking at these signals over time. Now I can actually go to the phase space and say, where am I on the phase space, and how can I get back to this circle? So this allows me to look at this also from the point of view of synchronization. Okay, any questions? Now, here are the interesting things. Now we start to abuse it. So Petros, we haven't actually tried the Reynolds number test, but now we started to test it with multiple vortices. Now, mind you, these cases were studied or trained only with a single vortex impacting the wing. Now, we're putting in two vortices, vertically arranged or horizontally arranged and impacting the wing.
That's a good question. So,
Yes.
so you have a vortex coming, hitting the wing,
Yes.
and then it leaves the domain.
Yes.
Then what is this? That's not a periodic thing, right? So why are these circles?
So these periodic things are for the baseline. So if it's transient, it'll go off the baseline limit cycle. Then as the vortex leaves the domain, it'll come
What
back.
do you mean the baseline?
Baseline would be undisturbed, just basically
Okay, yeah, that makes sense.
periodic shedding cases. Now, Petros, these are the lift distribution over time. Right? This solid line is the reference, and these dashed lines are the estimation. So it actually does a pretty good job. And this is for gust ratio 2 or minus 2.8. You can actually abuse this more. It does pretty well. And here is the decoded flow field, which is about 96% or 81% accurate, right? So we only trained with one vortex, but because the way CNN works really well, and this is a nonlinear autoencoder, it can actually reproduce the flow with multiple vortices. We actually even went more crazy because we're supposed to be flying in a turbulent environment in severe turbulence, right? Well, I don't know if turbulence is the right word. That's what the aerodynamics.
You can't talk about the turbulence at Reynolds number of 100.
Yeah. No. We're not going to do that.
I'm starting to be, I don't want to be nasty.
No.
I mean, it's Reynolds number of 100. Reynolds number of 100, you capture it with 2-3 degrees of freedom. You all know that. And so, what happens at higher end?
Yeah,
If
we'll
we
get
talk
there.
about
We'll get
extreme,
there.
right? I mean,
Yeah, we'll get there. But extreme is not from the point of view of Reynolds. Extreme is the point of view from the strength of the dispersion. So if you fly into 5 vortices, and if you fly into this kind of situation, which you probably don't want to, still nonetheless, you can actually estimate the flow field pretty well, right? And Petros, I'll make the argument that Reynolds number is not the biggest concern that we have, because these strong vortices that we're going to be encountering is going to usually have
what's the
lambda
Reynolds
force.
number of the vortex?
No. The Reynolds number that we're going to be encountering is not the issue. Reynolds, the vortices, the strength of the vortices is so high that usually they have lambda force that's straight from buildings.
What's the Reynolds number of the vortex?
The Reynolds number of the vortex, I mean, I'm defining Reynolds on base with 4.
No, vortex has a Reynolds number, which is a
Yeah,
circulation.
No. So this is probably going to be on the order of hundreds to thousands.
100.
Yeah. So I'm not arguing that this is turbulent environment. That's not the concern that I have right now. Okay. Now, Karthik asked about why these circles, right? So this is a transient problem, but let me take a step back and talk about phase dynamics for a little bit. And I've been interested in the concept of synchronization and also this concept called phase reduction analysis. And trust me, it's going to come together later. But there's a lot of analysis that's being done in the physics and biological physics community as to how you can actually analyze synchronization. For example, chemical reactions or jet lag. If you're thrown off let's say, time, which is also phase, you can actually go back to the original circadian rhythm. You can actually analyze how you can go back, right? Now, this is actually pretty nice. You can take a periodic flow, for example, or a periodic dynamics, and define phase. So if you have the full state dynamics defined as Q dot is equal to F of Q, we can define also the phase of that system. And phase, the time derivative of phase is omega, which is the natural frequency, right, of that periodic system. And if you were to look at what theta dot would be, the phase, you can actually define what's called a phase function, which is not just on the limit cycle, in the vicinity of the limit cycle, and is defined as a function of the state variable. And if you go through calculus, you can see that this is a gradient of the phase dotted with Q dot. And Q dot we have from the governing equation of the Navier-Stokes equation, which is the right-hand side of the governing equation. And if you take an inner product of your phase function and F, the right-hand side, that's your natural shading frequency, let's say in fluid flows. So for example, in well-over a cylinder, there's a dominant frequency. If you know where you are on this limit cycle in terms of the phase, you can always get back your state, right? Now what's nice about this analysis is that you can actually look at the influence of a perturbation that's added to the system. The gradient of phase function is actually called the phase sensitivity function. And if you take an inner product of this phase sensitivity function with a perturbation that you put in relationship to the phase, this actually tells you whether that forcing function is going to give you phase advancement or phase delay. Right? And if you go through this exercise, you can figure out how sensitive your flow field is to certain types of perturbation. And you can even go further to figure out whether you're going to get synchronization for a range of frequency and amplitudes, right? So some of you might have heard of Arnold tongue. You can actually get to Arnold tongue, okay? And this tells you whether you're going to synchronize to a sinusoidal input or periodic input or not, okay? Now, why do I care about this? Is because I need to lock on sometimes to a certain signal as vortices are shedding over my wing. Right? So here, it turns out there's actually a very nice way to figure out your optimal waveform from phase sensitivity analysis and figure out where should you actuate and how you should actuate over time. And we're going to actually compare this to just a simple sinusoidal input versus an optimal waveform input. Here for an example of flow over an airfoil, the leading edge and the trailing edge. And here's the difference. I'll just get to the point. If you were to put in a sinusoidal forcing input, it usually takes about order 10 cycles, let's say 6 cycles or so, to synchronize your forcing input. However, if you use the fast and trailing or optimal waveform, you can synchronize in about 1 to 2 cycles. So this is ideal because if we know there are certain types of shedding event, and if we know what the optimal waveform is, we might have a chance of actuating and have the effect be felt really quick, right? And what that translates to actually on the vortical flow field side is whether we can accelerate shedding or decelerate shedding. Now, we're still looking at this actually and trying to figure out how much force we need to get changes in lift, and it turns out it's actually not a small amount of force we even need to change the lift on the body. And that's expected because this is a pretty violent event, and we're having to work at making these vortices leave or stay on the wing longer, right? But you can change the lift behavior pretty drastically. Okay, so what does that mean? Let me now talk about a slightly different perspective about these vortical flows or extreme events. And now I'm going to be considering Reynolds number on the order of 10,000. So this is closer to, let's say, well, this I won't say fully turbulent, but it's certainly more turbulent than what we looked at. And this is from a PIV measurement with a flat plate wing flying actually through a gust. And this is a different type of gust. It's actually a jet of flow going from bottom to up. You can see it here. And you'll see the leading edge vortex forming, and it'll fly out of that jet. And the gust ratio, I believe, is somewhere around 0.71 for this case. Now, why are we looking at this suddenly after I talk about phase? Because now I'm going to take a slightly different perspective than just periodic flow. If you recall that we were originally flying from left to right with attached flow, and suddenly a gust hits from the bottom, and then we go back to the original state, we can actually think of this as a loop, right? You go from state 1 to 2, back to 3. So in our mind, I don't think it's too difficult to say that there is sort of a cyclic behavior from 1 to 2 to 3. Now, we wouldn't associate this with a Fourier type analysis because it is a transient flow field. But if you were to write it this way, perhaps we can define what phase is. Okay? And for now, there is actually a family or a community of research in the area of persistent homology. And this is pretty interesting. You can actually look at an n-dimensional system to see if you can form a loop. And I won't go into the details, but what it does is it kind of makes this hypersphere and see, as you expand the hypersphere, can you actually detect a loop in your system or your state map over time? And it turns out you can. In our system, there is a loop because you go from 1 to 2 to 3, where 1 and 3 are pretty similar. So it actually closes a loop, although this is a transient. You can take that information and say, well, can you go through a learning process to figure out what the autoencoder is, but with the idea that you're going to be generating this loop that you have gotten from homology, right? And it turns out you can. So now in this latent space now, it's a different latent space where we go from 1 to 2 to 3 to 4. Here is the PID measurements. We go from the wing initially without being any disturbance to a leading vortex developing, forming, and then detaching. And here's a reconstruction you can get from this type of autoencoder reconstruction. And actually, of course, it's not surprising that the mean square error of the reconstruction is really low compared to what you would get from something like POD. POD just can't get this, right? It wouldn't make sense to even try. Now, what's really cool is that you can apply it to a family of these experimental data sets where you have different incident angles and also different gust ratios. So here, this is kind of an interesting case. This is at a flat plate angle attack. If you were to try to increase the gust ratio, stronger jet hitting from the bottom, what you'll see is you'll still get the loop, but you actually go further out, right? The starting point is the same, but you'll go further out. If you change the angle of attack, then you can actually map out these loops at different locations. Now, with this perspective, we're now able to say that we have the concept of phase, right? And because we now have the idea of how to introduce optimal waveform for control, we might have a chance of figuring out how to control the flow or the attitude of the wing so that we might be able to achieve desirable lift profile over time. So for that, maybe I'll talk about the outlook side. We only talked about one type of perturbation, right? Or two types, actually. One is the vortex hitting the wing, and the other one is the jet hitting the wing. We're actually looking at different types of perturbations in terms of the wing motion as well. But there are a lot of different types of perturbations or disturbances in the atmosphere that we'll have to consider. So we're looking into now three-dimensional formations, or three-dimensional perturbations, three-dimensional wings, different types of flows. Right? That's something we're going to have to do, but luckily we have about 4.5 years to do this. And we're going to be extending our analysis to higher Reynolds number of flows. Thankfully, we have been fortunate to study these types of high Reynolds number of flows at 500,000 in Reynolds number. We know how to handle these, so this shouldn't be too bad. So in concluding remarks, I'm going to say a few things, but we started analysis and modeling and control of extreme aerodynamic flows. A lot of the techniques that we developed for turbulent flows, I think we're going to be able to use that to control or think about how to control these events. Let's see. Let's jump to the last one. However, I don't think we can actually think about control or stabilization of flight in the traditional way where we track sort of this nice cruise trajectory. I think we're going to have to change the way we think about it because the lift fluctuation is so large. I think the goal is more like we don't crash. And we don't know if the traditional flow effectors are useful.
flaps, trailing edge flaps, leading edge flaps, ailerons, they may not be efficient. So we might have to think about how to design the aircraft completely differently as well. Now, I think there is some hope. We're talking to some controls engineers as how to use the information about the manifold that we found, this cone-shaped manifold, so that we can go from point A to point B on the manifold in maybe an energy efficient manner or in a quick way. That there seems to be some nice theory in the control side that maybe we can leverage. And one of the other things that I haven't talked about today, but what Kai has found is that we don't actually need a whole full flow field to reproduce what's on the right-hand side. It turns out you can actually get pressure, you can replace it with pressure measurement, pressure sensors on the wing, only a few. I think he tried it with 8 or so, on the wing to reproduce the whole flow field on the right-hand side pretty accurately, while getting the manifold. So I think we have hopes in trying to get to not only estimating the flow field, but maybe predicting and also controlling in the future. So with that, I'll end my talk, and I'll be happy to take any questions.
Okay, thanks, Sam. Is there any question for Sam? I have a question actually. The phase sensitivity you showed. I mean, is there any relationship with the sensitivity?
There is.
Because it sounds, I mean, I didn't understand all the details, but it sounds like it's a sort of sensitivity around some sort of limit cycles or ish.
Yes, it's the phase sensitivity looks at more in terms of how you can synchronize to a certain path. But yeah, there's definitely a relationship.
It's something we started you were not in my talk, but I started my talk, and I'll repeat it. So we did also Reynolds number 100, and everything was perfect. We could get flow past the cylinder with two points in the latent space and all that. And then we took it and we did Reynolds number of 1,000, and it was garbage. Garbage in the sense that it is 20%. Maybe it's us that we don't know how to do this. But that's why I'm asking, it would be nice if someone else also does autoencoders, a Reynolds number of 1,000, 10,000, and what have you, and answers whether indeed all these representations are physical. That's why I'm suggesting that if you do 100, I don't think you can extrapolate readily even to 1,000 without doing all sorts of interesting things, in my opinion. Fix it.
Yeah, we'll have to
see. And I do this comment first to myself, because
Sure,
I also did 100, and I said great, and then I did 1,000, and it was garbage. So I'll be very interested to see it. And so
Right. So I have kind of two thoughts about that. First, we have to try it. We have to definitely test it. I'm in complete agreement with you. Now, the main concern for this particular effort wasn't the Reynolds, it was actually the gust ratio. So we actually tested on the gust ratio side pretty aggressively. So we trained from -4 to 4 in terms of the gust ratio, which is actually pretty violent, but we go and tested between ±10. It works pretty well.
When you are a Reynolds number of 100, you have enough dissipation to kill a lot of modes that the gust ratio at the higher end number.
But do remember, this is a transient problem. The time scale for things to get killed is actually not that long in these problems. Now, granted, this is different from Reynolds number 1,000,000, right? I completely agree with it. But if you actually look at these types of flows, even at high Reynolds number, the vortices and the life of the vortices at those time scales is actually pretty long, right, compared to the timescales that we're considering. So I'm not too worried about that, to be honest with you. And another thing that we are actually pretty comfortable with is if you use the CNN pretty well, it actually can be extended pretty widely across Reynolds. And that's something we've actually tested, not for this particular problem, for a different set of problems. As long as there are some features that varies in size but is present, we can actually do a pretty good job estimating where those flow structures are. So We'll have to test. We'll have to test, but I'm kind of hopeful. I'm optimistic about this. But I'm not saying that I can guarantee it. We're nowhere close to that, for sure. Peter?
I have a question from totally left field,
Sure.
but is rigid wing aerodynamics the best way forward to handle extreme winds? Because insects do very well with flexible wings and that's the size of the body.
Right.
So does this carry over to flexible wings?
That I don't know how to answer that. And because the insects are usually, I don't know if product is the right word, but they went through evolution process with what is it, objective optimization. So I have a feeling that they cannot also break the structures, right? And you could likely break structures at this high of a fluctuation in terms of the force being applied over a short time scale. So first, it might be the best way to go forward with flexible geometry, and also it might be better for the safety and the longevity of the vehicle too. But I don't know the answer to that.
So when you plotted the manifold with the C1, C2, C3, so are you assuming that those vectors are orthogonal in the latent states?
No, we don't assume that at all.
Okay.
And in fact, we can't assume that.
Exactly, yeah, right.
And to make it even worse,
Yeah.
they're not unique,
Yeah.
right?
Yeah.
So that's the challenge here. And I think we're going to have to change the way we think about this, because do we really need orthogonality? I'm not sure. Right? Those are nice properties for sometimes analysis, but just for the sake of compression, we don't actually need orthogonality. Right? Those are nice features. I'm not going to argue about that one. But that's to be seen maybe as we go forward.
But still, if you use these three, because you plotted against these orthogonal bases anyway, you put, physically the axes are orthogonal in the plot.
Just the way we plotted it, right?
But what are we looking at there? Because if I look at the sort of thing, I would assume, okay, it's sort of a Cartesian frame, frame of reference, which is sort of global, but they're not called linear coordinates, but they are called linear coordinates, C1, C2.
So if you think of this from an oscillator point of view, you do need two axes to get something like a sine or cosine type behavior, right? So to me, it makes sense that if you want to get oscillatory behavior or circular behavior, you do need two axes. Now, if you do, you also want to distinguish these different cases, right? Because if you don't have the third axis and it collapses all on top of each other, there's a danger that you might overlap these circles on top of each other. And when you do so, that means if the two circular paths overlap, that means that you can't distinguish the different angles of attack, right? So it's natural to me, or at least maybe in post-processing way, is that this axis are needed to distinguish the different incidence angles, right? By the way, I said this is a cone shape, but it's actually an hourglass, because if you go to the negative angle of that, there should be a similar structure, a mirror image structure.
I have a comment about the hybrids. For compression, I agree that doesn't matter. We might compress better if those latent vectors are not allowed. But if I'm trying to learn something in the latent space, for example, generalize how those vectors variables, then this entanglement is interesting.
Right, absolutely.
In this case, I guess the parallax is not easily, but orthogonal to the others because you are providing the different parameters for each case. So you're already creating a data set that has different cases that are differentiated by the angle of attack. Would you expect that if you train the same thing only on one angle of attack, then you can reduce it to two variables only, and then see this circle, or just like if you train the open only for one thing, angle of attack?
We haven't tried that, but I assume you're right. I think you're going to be. I think you're correct that you can probably get everything to collapse onto a surface, right? A two-dimensional plane. I think you're right. Yeah, we haven't tried that though. That's a good point.
Is there any final question?
Maybe I should follow up with that. I mean, in what circumstances would you not get a closed curve in any vector space?
I mean, so here's one thing that I haven't thought about, and this is something maybe that builds on Petros's comment, is that if you have a higher Reynolds number, and if we're not going to get a perfectly closed limit cycle, then this is going to be a blurred sort of a attractor, right? In those cases, we won't get a circle in there, right?
Are you considering the undisturbed shape? Those circles are undisturbed.
Yes, yes, yes.
Vortex shape.
Right. So for the disturbed
That's
case,
theoretically,
right.
you're going to get blue.
Yes. But for the disturbed case, you would say for this Reynolds number, you start with the periodic case or just steady case, and then you get disturbed, but then you'll go back to the limit cycle, so it'll be periodic. So in those cases, it will be a closed circle.
Why is it called? Why do they become larger? That's the explanation that they become larger.
Because there's more fluctuations as you go higher in the angle of attack. Because the vortices are much bigger as you go higher. And you can also, go outside of this cone if you have a large vortex hitting it. It can either go upward or you can go slightly outward or inward. Because the autoreporter is also trying to capture the variations in the flow of the vortex.
Okay, if there are no further questions, so let's thank Sam once
Thank
again.
you.
Thanks, Sam.